It's my great pleasure to welcome you all back for our first quote of the semester and introduce our very own Professor Dan McKinsey. Dan's recognized as a leader in one of the most exciting fields in experimental physics, the experimental measurement of dark matter. Dan received his PhD from Harvard in 2002, and after a postdoc at Princeton, joined the faculty of the Yale Physics Department in 2003. Dan came to Berkeley as the Georgia Lee Distinguished Professor of Physics in 2015, and since coming here, he's conducted a world-leading program of research primarily focused on exploring the potential of liquefied noble gas for dark matter detection. In recognition of his contributions to the field, Dan was honored as a fellow of the American Physical Society in 2017. Today, we're fortunate enough to have Dan here to tell us about the first results from LUX-ZEPLIN. It's the largest and most sensitive liquid xenon-based dark matter detector ever constructed. And we'll learn about what these results can tell us about dark matter. All right.
Thank you, Bill, for the kind introduction. And we'll get going. Okay, can you hear me okay? So I'll be talking about the LUX-ZEPLIN, and here's a photo of a lovely area where it's located in the Black Hills of South Dakota. So I only have a few slides about the motivation for dark matter, but very briefly, there are many lines of evidence across distance scales in the universe and going back in time for qualitative and quantitative arguments for why dark matter has to exist. One of the most striking comes from measurements of the cosmic microwave background, where the power spectrum and the ratios of power in different angular scales tells you the ratio between the amount of matter that's crunching down gravity versus bouncing back due to electromagnetic forces. If you look at the amount of small scale structure in the universe, and that can give you the total amount of pumping that you need in order to form the galaxies and other structures that we see. And you can compare that to the amount of light element production in the early universe, helium-3 and helium-4, and lithium and deuterium, that tells you the total amount of ordinary matter, baryonic matter in the universe. You compare those two, you get this striking difference between the total amount of gravitational matter and the total amount of stuff that's made of neutrons and protons and electrons, and normal matter in the standard model. We'll have to look at galaxy rotation curves, the velocity that stars are going around the galaxy, or the velocities that galaxies have around each other in galaxy clusters. And also, very strikingly, you can look at how light is bent around galaxy clusters, galaxies, and thereby image where the lens is, where the gravitational stuff is that's lensing the light to let us map out the distribution of gravity producing stuff in the universe, and that also points you to large amounts of dark matter. So there's a clear and multifaceted evidence for the existence of dark matter. And what the dark matter is a central puzzle in particle physics and astrophysics. The standard model of particle physics can't account for the dark matter. And that, to me, is a very clue that can lead us to new principles, new theories beyond the standard model. Maybe the candle under the tent to get us insight into what are some new kinds of fundamental physics to push the field forward as a whole, leading to new scientific questions. So here's a couple of pictures of, if you look at the speed that stars are going around galaxies versus the distance from the center of the galaxy, you can see very often these sort of flat versus distant velocities that gives you evidence for a lot more matter in the outer parts of the galaxy around which stars are captured and moving around at high velocity. Here's an example, the so-called famous bullet cluster, where if you just look at the lensing and the distribution of lensing, you can image the lens, which points to two gravitational potential is. That's where most of the dark matter is, and you can compare that to X-ray images, basically telling you where all the dust is. In fact, in this case, and there are many other cases like this in the universe, the dark matter and the ordinary matter can actually be spatially separate. So to summarize, it turns out that the dark matter has to be about 27% of the energy composition of the universe. It has to be stable. It has to have lasted since the Big Bang. It has to be electrically neutral. If it has even a small charge, it would get kicked out of galaxies. It has to be non-baryonic because it was the early amounts of light element production would be off. It has to be non-relativistic in order to get the formation of structures that we see. And if you put all this together and you do observations on the Milky Way, velocities of stars on the Milky Way, you get an estimated local density on Earth of about a third of a proton mass per cubic centimeter. And this has to be some kind of new particle beyond the standard model. And so there are various candidates. One of the ones on today is called the WIMP. Others are called axions or dark photons. There are many, many theories that theorists can come up with for what the dark matter is. Okay. But to focus on WIMPs, which is the main thing we're searching for in the LUX-ZEPLIN experiment. So WIMP stands for weakly interacting massive particles. For a long time, large black hole objects and looking through microlensing. And the acronym there is MACHOs, a big object MACHOs, massive compact halo objects. And if it's the alternate acronym was maybe astrophysics can help. And then WIMPs is weakly interacting massive particles, but the alternate acronym is well consistent. So this particle, right, if it can only vary with interactive matter, it's dark matter. Massive amounts in the Big Bang, and it turns out it can non-relativistic freeze out. And I'm not going to go through the algebra here, but it turns out that if we have a particle at the weak scale, interacting through the weak force, that is the W or Z, it gives you the right interaction strength and mass in order to plausibly be the dark matter particle, something called the WIMP miracle. And then it could exist today about what we need. Also supersymmetric extensions to the standard model. And there's a particle in that language called the neutralino, which would be some superposition of the photino, xenon, and Higgsino, supersymmetric, as yet undiscovered particles. That could be the dark matter. And this mass range could be something from the proton mass to thousands of times the proton. And that can easily, these kinds of models can easily give you the dark matter particle. But a key thing is that these particles need to be charge neutral and stable, and that's what example is. Also, universal extra dimensions can give you similar large stable particles. Just a few examples. So in this WIMP thermal relic, would be sort of in this mass range of GeV to 100 TeV mass, that is between the mass of a proton, roughly, and 100,000 times the mass of a proton. So think of yourself, think sort of nuclei masses. And so there are a number of these models. If you're interested, I can give a nice summary from this recent working group in the SOMAS process. Here, you can look at it online. But the key thing is that right now, this field is probing many of the most interesting models that have been produced over the past 20 years. And here's just some examples. Here in gray is regions of cross-section mass parameter space that's been ruled out. That is, if you don't see a bunch of events, you rule out cross-sections above. Otherwise, you would have seen some events. If the cross-sections were higher, you would have seen some. Below it are regions that are still being explored, and here are some models that you can be looking for these possible. And as I'll describe as we go, what we're coming up against, maybe in 20 years or so, is something called the neutrino fog, which is that there are neutrinos flying around us, going through us and going through the Earth. Occasionally, those neutrinos could scatter from our detectors, and unfortunately, we can't shield out neutrinos, so they can present an irreducible background in our experiment. So it's very difficult in the long term to go below this blue line in our experiment. I'll come back. Okay, so if you're looking for WIMPs, you're looking for nuclear recoils in a low background detector. Okay, and you're looking for a rate that looks like the number of particles in your detector, n times some density of dark matter, rho, times some typical cross-section and velocity. Now, the velocity of the dark matter particles is roughly, on average, similar to our sun's velocity around us. Either of those velocity scales give you about a 10 keV energy deposition when one of those particles scatters from a nucleus, very roughly. So we're looking for these very rare events, but it's a nuclear recoil. Okay? Keep that in mind. So you need low radioactivity, low background in your detector. In practice, in order to have low background, you need to be in a deep underground laboratory. This is to get shielded, to hide from all cosmic rays that are raining down on the Earth and creating radioactive nuclei in us and in the Earth crust. To get away from that, you have to go deep underground to get the lowest levels of radioactive background. You also need a low energy threshold. Here, the 10 keV, which is a small energy compared to most particles of the experiment, or X-ray sort of energy. And because our signal is a nuclear recoil, but most of the radioactivity around, most penetrating radioactivity is from gamma rays. If you have some technique where you can tell the difference between a gamma ray, say, and a nuclear recoil, then you can be ahead of the game. And if you have all those things under control, then scalability is important. That is, having a detector technology with math to look at these larger N to be able to probe smaller signals. Okay. Now it's really a sort of a hotbed of technical innovation. There are various technologies, and I won't talk about indirect detection, where you're looking for dark matter colliding in the cosmos and spitting out standard model particles. I won't really be talking about the collider experiments where you bang things together at the Atlas or CMS to try to produce dark matter particles. I'll really be talking about direct detection, and these are, by these scales, relatively small experiments, sort of table or room size experiments. Dark matter particles scattering from nuclei in very low background particles. And typically for these WIMP detectors, it's common to look for a couple of different signal channels. Like you might look for a heat signal in your detector. You might look for some charge that's released in your detector, or you might look for some scintillation light that's produced. So a lot of the most effective techniques have involved looking for a couple different signals. For example, the superseding EMS program for decades, and has been very successful in using heat and ionization, looking at the ratio of those two signals to search for dark matter particles and reject gamma ray background, which gives you a higher ionization to heat ratio. You can also look at heat and scintillation, for example. The test experiment uses that technique. What I'll be talking about are experiments that use ionization and scintillation. So we look at the ratio of charge that's produced to the amount of scintillation light to give us event by event identification. Is that a gamma ray? Is that due to a beta, or is that due to a nuclear recoil? And that helps you get low background. Okay, and there's a lot of support in the community, in dark matter, in the particle community, to look for the dark matter particles through direct detection. And the mantra is to delve deep, looking into lower and lower cross sections, pushing down into the neutrino fog. And now there's sort of another mantra, which is to search wide, look at a variety of masses and interaction types. I'm going to be really focusing on this delve deep version, which is what we do mostly with the xenon method. But it's also nice that this field really crosses boundaries. We're interested in what's happening in the astrophysics to give us a better clue about where to be looking for the dark matter. We're interested in new technologies coming from our friends in nuclear engineering and nuclear physics to help, because we were looking sort of at nuclear scales. And there's a variety of different technologies that we use. We try to be clever on the technological side to get you good signal and low. A lot of, and one piece of that experiment that I will not be talking about today, other than this one slide, this could be its own colloquium. But we also have a separate project of Tesseract, which includes the SPICE and the Herald detectors to look for dark matter particles in mass dimensions. And this is a program that's complementary to the LUX-ZEPLIN project that I'll be talking about for the rest of the colloquium. But just the flag that there's also lots of great work going on here in Berkeley, in Matt Pyle's group, and collaborators up the hill at LBNL, as well as our collaborators across the country on Tesseract to develop new technologies to very low and dark matter. Okay, but as I said, I'm not going to talk about this today. I'm going to talk about noble liquids and the LZ experiment. So why noble liquids? Noble liquids we mean like liquid xenon, liquid argon, liquid neon, liquid krypton, liquid helium. Why do we like these? Because they're relatively inexpensive, they're easy to obtain, and they're dense, so it's 1 to 3 grams per cubic centimeter. A key point is that they're easily purified. You can, because they're noble gases, you can do something that'll cause chemical reaction. You can remove the junk, the impurities that are in a noble liquid very effectively. Because the noble gases, the lighter ones have a further bonding, you can purify them very easily using charcoal. For the heavier noble liquids, you collect ionization electrons. You can drift for meters through liquid xenon or liquid argon or liquid krypton without these electrons being absorbed. And they have very high scintillation yields. Noble liquids, they don't absorb their own scintillation rate. So you can build big detectors and still create scintillation. As I'll explain. And that scintillation light yield is still pretty good even for nuclear recoil. Most detector materials, the nuclear recoil signals are quenched very heavily. They're still quenched in noble liquids, but not in most materials. Okay, it's basically a big liquid. It's pretty straightforward. You want a bigger detector, you buy a bigger bucket, you instrument it, and you have a bigger detector. Here's some comparison of basic properties across noble liquids. Okay. Each of these, actually, I've worked on noble liquids in various areas. Each of these is like an old friend with different quirks and foibles properties. Krypton is the most radioactive of them. So in practice, we don't use it for low background searches. Krypton 85, Krypton are in our atmosphere at high enough levels that if you had a kilogram, there would be 1 million events per second in the krypton. Even krypton, in fact, it's an impurity we have to measure. Argon is slightly radioactive, which in our business is still a big problem. It's slightly radioactive, but it's cheap. You can get a good penalty with it. Neon is free radioactivity and reasonably dense. So actually an interesting material for a low background, but you can't drift charge through it easily. And helium has lots of wonderful properties. It's a super fluid and cold, which leads to all sorts of interesting detector techniques. We're really focusing on liquid xenon, which is the heaviest, as well as the highest boiling temperature. It has very high scintillation yield. There's a scintillation wavelength in the vacuum ultraviolet, and it's a pretty fast scintillator. The slow time constant 30 nanoseconds. And it is intrinsically low in background. The only thing you can tell is long and radioactive is xenon 136, which only decays by double beta decay and has an enormously long half-life. Xenon radioactive, but in practice, you don't have to worry about very long lived. So if you have an event in xenon, it's xenon atom. Actually, this means any noble gas, really. And you also can ionize it. If you excite it, that can form some dimers, and that could quench. And there are various processes here. We can lose heat. In the end, you end up with some electrons escaping, as well as some dimers, like in this case, xenon 2 molecules that are produced out of the scintillation, out of the excitation. And then those scintillating molecules are in singlet states, that is, where the electrons, outer electrons are either in a singlet state, or they can be in a triplet state, and those have different radiative lifetimes. But either way, you get 2 ground state atoms and a photon. That's the scintillation. Okay. And here's some of the scintillation bands that you get from these different liquids. Here's helium in red. Here's argon in purple. In green here, we have krypton. Here you have xenon. Okay, and one nice thing is if you look at a synthetic quartz or a sapphire, the scintillation of the xenon is higher wavelength, so it can actually get through those windows. Okay. And this means you can use photomultiplier tubes with the right windows in order to collect the scintillation. As long as it has transparent enough window and a photocathode that's sensitive to these wavelengths, you can use a photomultiplier tube, which is sort of a really workhorse technology for large scale detectors. Okay, the density is high. You photoabsorb gamma rays very easily. You can also count and scatter them well because of its high density. Has high scintillation and ionization yield. The ratio of scintillation and ionization is different for gamma rays versus neutrons. You can get very high purity. The cryogenics is not too hard. So that, minus 100 degrees. And here you can see a picture of the xenon scintillation response. You don't have to worry about impurities like water or oxygen that can absorb that scintillation light, but in practice, you can reduce those impurities low enough that you can collect the scintillation. I have to say, when I started in this in the early 2000s, it wasn't so clear to us and to the community that we would be able to get sufficiently good purity in real big detectors, but it turned out that we could, and allowed these really large, very sensitive experiments. Okay, so how does the two-phase whiff detector work? This is the principle behind the detector. If you have a particle that comes in and scatters in the liquid xenon, it makes a scintillation light pulse. The light from that scintillation then can be collected by photodetectors that are inside the xenon. So here in the bottom, there's an array of these here, immersed in the liquid xenon, and it can collect that scintillation light. The light can internally reflect off the top surface. There's a sort of a liquid xenon, gaseous xenon interface up here. The internal reflect, in fact, a lot of the light ends up in the bottom array. Some of it can make it to the top array as well in this S1. Okay, so you can get electrons out of the track. Those electrons, we drift with an electric field. We drift them up to the liquid gas interface. And at that point, we extract the electron into the gaseous xenon. And in the gaseous xenon, those electrons hang on atoms and make them fluoresce. So the key thing here is that we don't have such a high field that we get a breakdown in the gas. We just have enough field that the electron will excite xenon atoms and give you a very nicely linear response without much fluctuation. That signal is called S2, and As you can imagine, if you get a cloud of electrons that pops up, it'll make light near where those electrons popped up. And that light will be concentrated mostly in the PMT right above it. So the distribution of light in the top PMT array tells you the XY position of the event. Where in the right and in the down where that event happens. And then because we know the electron drift speed, you can get Z, the depth, based on time. Okay, so we get 3D position information for every scatter that happens in the loop. Okay. And that's especially because if you have a big enough detector, the gamma rays and the neutrons can be forced to multiple scatter. It can be shielded out by the outer part of the liquid xenon. So if you have good position reconstruction, you can pick out the middle of the detector where the backgrounds are lowest to look for the thing. Okay, so I'll say a little bit about our last experiment. I talked about it on a film back in here in like 2015 or so. But I'll very briefly talk about LUX, which is the predecessor of LZ, versus collaboration. Located underground in the Stanford Underground Research Facility first in Lead, South Dakota. Pronounced Lead. The lead is where the beginning of the gold vein is that you should follow to collect all the gold. That's the pronunciation. And it's a nice depth, 4,850 feet below the surface of the Earth, which turns out to be about sea level, because you go up into South Dakota about 5,000 feet, and then you go down, and when you're working in the lab, you're at about 3,000. And here's just some photos of LUX. It was built. And with April, with a spokesperson, had about 100 collaborators. And at the time, between 2013 and 2017, was also more sensitive detected in the world. Okay, what really made these experiments work is self-shielding. This idea that you can use the outer part of the detector to shield the inner part of the detector from radioactivity. And so this, in the early 2000s, many water-based detectors have been very successful in using that technique to get very low background to look for neutrinos. As well, lots of organic-based experiments are doing the same. Cam Lamb had a lot of folks collaborate on it here in Berkeley. The Borexino experiment, we're using the same trick, that is, mathematically define part of the detector in the middle where the background is actually low. And so in the early 2000s, people interested in dark matter and also looking in neutrino physics realized that maybe you could use these noble liquids to do the same trick, build a big detector with a fiducial cut to get the lowest background in the middle. The first conceptions of using self-shielding to get really low background. Skepticism at the time, could you really have low enough internal background, low enough energy threshold, good enough position reconstruction? But since back here, when small, precise, clever detectors were the norm, we've really gone to big and just smart enough detectors to look for them. It's really been a feature. And here's just the idea. An MEV gamma ray tries to get in. Right? And remember, our signals are in the KeV range, lower energy. So if you have an MEV gamma ray, which is the most penetrating gamma ray, that we can worry about, suppose it makes a KeV deposition. That means it only scattered at a small angle. Now it's trying to get out the other side of the detector, having only made a small scatter angle. Now it has to basically, that gamma ray is effectively having to traverse the whole experiment, only scatter once with a small energy deposition. And this is really not if the gamma ray has to penetrate through this outer field part, it really has to get through the whole detector, only scattering once. So the chance of that happening is dropping like e to the minus the size of the detector over the scattering. It's really heavy success. And that self-shielding is what made that work. Anyway, we had various searches through 2015, 2017. At the end, we put we decommissioned LUX to be able to put in LZ, and we put LUX in a museum. So if you're ever in the Black Hills, you can see LUX in a museum there that's about the lab. Here's a photo of the laboratory underground. All the HVAC, power, and here's a photo of LUX when it was first installed in 2007. Now here, if you look at S2 versus S1, the nuclear recoils are printed on this red line, the electronic recoils with this band printed on this blue line, and the relative lack of events in the red band allowed us to set a limit in dark matter cross-section. And this is what we expected, sort of a few events total, what we expected in the red band. We did a likelihood analysis, and this is what we were able to do at the time. This is late 2016. It came out with that constraint on these sort of dark matter particles with mass between 5 GeV and up to 100,000 or so, including cross-section stuff. Since then, various competitors, Panda X and Xenon, were able to go further, including even lower cross-section. In the meantime, we looked at the LUX data. We did a few additional searches. I just want to highlight a couple of them that Berkeley folks had a big role in. One was a sort of search for sub-GeV dark matter called the so-called Migdal effect. That is, there's this effect where if a nucleus gets a kick suddenly, you have a sudden shift in the position of the nucleus with respect to the electrons. And that is sort of a sudden approximation it can yield an electron that's ejected from the atom. It's an inelastic process. You can actually get out more energy than you could just through a nucleus. And so you can search for those elements and put constraints on sub-GeV dark matter. And for LUX, because our energy threshold for electronic recoils is actually lower, like 1 keV compared to 3 keV for nuclear recoil. So that allows us with tighter constraints on low mass darkness. Here's some spectra for what you would expect for nuclear recoil at a certain mass, 400 MeV, or 1 GeV, or 600 MeV, or 5 GeV. You can compare what you expect from the recoil compared to the signals you get from the Migdal effect. And so by looking in the electron recoil band, we were able to search for these sub-GeV dark matter effects. This is the result that came out. Ends up being the thesis of nuclear. And so, of course, many other experiments followed suit, looking for the sub-GeV effect using the Migdal effect. And now that's sort of a pretty standard thing with all these collaborations too. Okay. Also, like another result from LUX that we had Berkeley. One is studying this discrimination data, or how well you can tell a nuclear recoil from an electronic recoil. So if you look at the energy partitioning, how many excitons you get versus ions, electronic versus nuclear recoil, you get a lot more here in the exciton band for nuclear recoil than you do for an electronic recoil. And so the ratio of these tells you whether you've got an electronic recoil or a nuclear recoil. Unfortunately, their effect is scrambled by recombination effects. That is, ion can grab an electron, and the statistics of those fluctuations can make it more difficult to tell the difference. So the question became, how do we best suppress these so-called recombination fluctuations? And so we did a big study in LUX data over a variety of electric fields to study what the best field should be in one of these detectors to get the best background result. Okay. We looked at various fields within the LUX detector based on position for both electronic and nuclear recoil, and did a study that it showed that the ER leakage fraction, that is the fraction of electron recoils within our energy range that could be mistaken for nuclear, was minimized at sort of 2 to 300 volt per centimeter. Okay, and this became an important aspect to feed into the design of future things. So give us something to shoot for the field in LZ. Okay, so I'll start going into LZ. The Zeppelin experiment. Zeppelin was a long-standing program in the UK to look for dark matter particles using liquid xenon. So LUX-ZEPLIN is basically signifying a merger of two large collaborations, LUX and Zeppelin, to do an experiment. And here you can compare what we were able to do in LUX in 2017 was what we designed and calculated we should be able to do with a large liquid xenon detector, about 10 tons of liquid xenon. And so you can see where our projections. You can also look for dark matter scattering from the spin, neutron and proton spin, and what projection sensitivity we have for those. And so LUX went into a museum here, and there I am, 5 years ago or so. And you can see it. And here's the scale of LUX going up to LZ, and a picture of schematic picture of what we thought it could look like. One important addition was not just a water shielding tank around the cryostat, but actually a layer of organic scintillators. And the organic scintillator could be used to detect lower energy neutrons and gamma rays produced in the experiment itself. It's a way to veto those backgrounds. There's an additional handle and way to reduce background. The Zeppelin experiment was an expansion over the 35 institutions, 250 scientists. These are listed institutions. In the U.S., supported primarily by the Department of Energy, the energy system. It also support an excellent group in Portugal and also in the UK. So the plan was scale it up, make it more like 1.5 meter diameter, 1.5 meter height, 7 tons of active xenon, lots of Teflon for light collection, about 500 PNTs that are made to run at this lower temperature and collect the VUV scintilation light. Various grids, the cathode grid that gets the the so-called gate grid, which is just under the liquid surface, the anode, which is just above the liquid surface in the gas, to find the kind of rejection. And here's some photos that are coming before 2019-ish here. Okay. And the assembly of the full PPC. And I have to say, this was built in much conditions than LUX was, because we really wanted lower back than we got away with in LUX. Huge effort on keeping everything dust-free. And that is basically to keep the radon levels low enough for this thing. And so tens of thousands of ultra-clean, low background components came together. And a huge part of that effort was here at LBL. Key arrays for LZ. Here's the PPC coming together. A few moments. And here's just a half of those. One bit is actually liquid xenon skin around the PPC. So it's a layer of xenon to look for scattering. Well, organic scintillator detail around that we call the outer detection. The outer detection is especially good at detecting neutrons. When neutrons are lower in rate, but especially worrisome because they can more easily mimic a dark matter. So a huge effort going into mitigation of various background sources. All the technical for assay, how many gamma rays I don't know. A huge effort into making sure that our background matter is low enough in this enormously complicated science. We also got contamination of the xenon itself. And here's sort of a timeline. We proposed it, and we built came together with our technical design and got the so-called CD3 and scale for the PNT arrays. PPC complete 2019. Of course, you know what happens in 2020. Life gets very difficult because of COVID. And everything slows down to be safe. But we still, through 2020, 2021, we're able to finish completion of the detector, fill it with liquid xenon, and then in 22, we begin science operation. I'll just show a lot of photos. So here we go. Outside, you can zoom out. The grid, which happened at SLAC. And is actually the grid directly woven so that we didn't want to just have one wire straight, because if one wire broke, then you're lag and then going out the detector. So we actually built the detector using woven grids that we wove ourselves. And even after that, it was 15. Going into the biostat, PPC underground for installation. And here it is, the PPC down underground. Okay. About to go into the biostat. And now I want to do a little sub-bar on the electric fields in LZ, because this is another area where Berkeley had a big impact. So turns out that uniformity of the electric field matters a lot. You need good position reconstruction because the amount of charge and light you get for different events very strongly with energy and electric field. You really want a good uniform detector in order to get that detector performance without doing a huge amount of calibration. And as I said before, we figured out that the optimal field is around 300 volts per centimeter in the liquid xenon to get the best background result. Okay. So here at Berkeley, UC Berkeley, we put the job on of attaching the high voltage to the cathode of the experiment, the highest voltage part. And the typical approach before that was to have a high voltage cable running down all the way to the cathode from above, and then make a connection. And the problem there is that if you have a high voltage feed coming down, it is going to create very high electric fields. And you know about neon lamps, right? Xenon lamps, all these different noble gases, if they have too much of high of a field in them, you can easily get breakdowns in light production. And too much light production would mean you'd be blind to the dark matter. Okay. So the approach we took instead was to have a high voltage feed by that. And this was totally new in this area. We did that so that we wouldn't have to come to have a very constrained biostat. So something inside this space to work with. And be able to do things on larger scales and keep the electric field strength lower for a given voltage. So you end up with this complicated system where you have a cable coming down to gaseous xenon, into liquid xenon, and then you come down, and then a grading structure in order to very gradually bring down from the ground and down to the voltage of the ground without creating very high voltage. And so we designed and such a rejection to enable that control of the high voltage. And this came in through that in vitro, you see, and as well through the organic solar vitro. And we did lots of electric field things to figure out where the highest fields would be to keep us going. There's a bunch of prototype testing, basically building prototype versions of that high voltage feed, testing them in liquid argon, make sure it wouldn't get a lot of light produced with the system when we attach it in liquid xenon. Because if we attached it in the real experiment, the problem, it would take years to take it all apart, fix it, and come back together. So it's really important that this works. We did lots of testing before. Here's some photos of the construction at LBL. Ethan Bernard is a project scientist who watched it as a graduate student, just worked on high voltage speed. There's a construction, various bullets the high voltage speed came through, and how it shipped. Big box here, South Dakota. Here it is being installed in the water tank, and inside it was underground, and inside the thing is filled with water. Here it is going in. Oh, there's lead, attaching it to the cryostat, and the cathode connection where it's made. There's a free connection made between that grading structure and the cathode, and that high lead there attaching the high voltage. And here they are, and it was all sealed up and ready to go. So this happened in like March 2020. Okay, just as COVID was hitting, we were able to seal it up and go back to here's everything closing up, March 2020. And then we had many months of pumping on the detector, making everything clean, installing the outer detector, these big acrylic tanks that would get filled with organic minerals. Okay. More photos of the outer detector and the photo tubes that read out the scintillation light from the detector. And here, lots of electronics, all those PNC channels. I have 10 minutes left, so I'm going to move faster. There's lots of xenon circulation systems to remove all those impurities. And also krypton from all the xenon, down from sort of part per billion levels to sub part per trillion levels, but before it's stuff the photo. This is done with a krypton removal system based on charcoal that was built at Scott. Also electronics, all those PNC channels get digitized, all the data gets analyzed offline, with NERF, up to here. But you can see there's sort of highlights what events look like, an S1 pulse and an S2 pulse. We were able to get up to 90 volts per centimeter, 33 kilovolts on the cathode, which we were very happy with. So we were able to hit a field close to what we wanted to for the operation of this thing. That really came from the big effort in making both the grids work well and the high voltage feed. Operation characterization, exact, after initial calibration. After that, Smith, 2021, we were able to start the rig switch and get going in 2022, and by last summer, it was these first results. Okay. So, and then the anatomy of the event, you get an initial pulse, which is cartoon, here's real data. We did a ton of different calibrations. We fast neutrons, we actually dope the detector with tritium, and then remove it to get lots of data decay events in the experiment. We use other monoenergetic sources like MCN and 31M, and then also various background sources in the detector. On lifetime was really stable, about a millisecond, way above our requirement of 1 millisecond throughout the run. We're quite happy with that. The purification system was well. And we're able to calibrate and map out the electron recoil and nuclear recoil bands with tritium and with fast neutrons. And we found that we were able to get 99.9% rejection of electron leakage. Below the median quantile of the 40 units. So that was substantially better than our 99.5% requirement that we had from the beginning. So data quality, before you look at anything, no single scatter cut. This is you get quite a big mess. If you look at S1 versus S2, start picking out a fiducial mass. Start seeing it cleaned up a bit here. Still a lot of stuff here at low S1. But then there are various data quality cuts. Space cuts, cutting the events based on the time period cut, where the detector was not pretty stable. In the end of it, we were able to keep our 50% acceptance for low spot frequency recoil. And you can see the efficiency versus energy that we're able to get and benchmark against all our calibration sources to make sure we're getting a good stuff. What kind of background we had to worry about is if there was a big pulse, then electrons could be released from various impurities and rigs. And so an important cut for us was that if there was a big pulse, that we wait for a millisecond or so until we could look again. There's lifetime. You can see how our lifetime built up over 22. Here's some of the background about the data decays and resolved electron captures from gamma rays to the detector materials, from positive neutrons, solar neutrinos in principle are a background. And one thing we worried about a lot here at Berkeley is so-called accidental coincidences. So here's radon, which is an important part of the background. Another thing that we realized and led a study here at Berkeley was that argon-37, which is isotope about a month half-life, could be produced when the xenon's at the surface. And so one of the postdocs here at Berkeley did a study that showed that the argon-37 would still be sizable even after we took the detector underground. Now it decays away over time, so eventually this is not an issue. But in our first run, it was still important. And so, not having looked at any of our data, we predicted what the rate of argon-37 should be based on some nuclear modeling, and expected about 100 decays of argon-37 in our first phase. So argon-30 is large, in fact, but still, not here. Before we looked at our another thing we looked at quite a bit here, the accidental backgrounds. If you have an S1 pulse that's isolated somehow and a random S2 pulse, those might pair up accidentally and create an event that looks like a dark matter. And so we expected over the full range of S1 and S2, so about one event. So really work hard to get that down and create some new cuts in order to reduce the isolated S1 and isolated S2 background, so that when you combine the two, you wouldn't get an excess background. Okay, if you look at the background only expectation of the data, you get this combination of events. Okay. And this is what we saw in the data. First, what the instrument look like, where they should live, and all the right on recoil. Okay. And here, if you look at position space, where the various events were, pretty uniform, all because they're on its. And here it is versus energy, event rate versus energy. Here's the argon-37 peak, which was there as we predicted. And here's the overall combined background. Again, for the various background sources, comparing the expected in the events to the best fit. And so the performance overall was about predicted it should be. And so the computer, all systems go for continuing running for the next 4 to 5 years. You can use this data set to say something like dark matter. In fact, the standard in the field, you use per cubic centimeter. Its velocity is V0 that we're going to the Milky Way in, and some escape velocity for the Milky Way. These are basically standard assumptions in the field. With those, we were able to set this new limit for spin-independent neutron. That's here in black, and in the dashed gray, it shows our expected sensitivity, given the background that we saw. And so compared to the existing strongest upper limits, we now have about an improvement at 30 GeV and about a factor of 1.7 improvement at high max. So even our very first run, we were able to set the best limit on WIMP stuff. But we're just starting. We'll be able to go quite a bit as we continue running LZ and getting bigger and more sophisticated analysis. So, and so not just WIMP, we can do all sorts of other science. We can look for spectral for dark matter, such as really pioneered here by the Pascal group. You can look for solar axions and ALPS. You can look at the lower mass dark matter particles, leptophilic dark matter, mirror dark matter. You can even look for neutrinos that will data reasonably competitively. Our energy resolution we already see in LZ is better than any achieved in our liquid xenon-based detector, at about 0.6% at the double beta state. So dark matter is one of the biggest mysteries in particle physics today. Very commonly mentioned topic in the SNO mass letters of intent. And in the future, we're going to keep probing deep in cross-section space to try to detect the WIMP. Other technologies we're pushing toward lighter masses. But overall, we expect this sort of Moore's law improvement in sensitivity over the years as we get down toward the neutrino side. And here's where we were with LUX and xenon 1 and here's where we expect to be with LZ in the future XLZ vehicle. How much time do I have, Bill? I'm on negative territory now? Okay. Just one slide, we were building, we're creating a new collaboration. We're merging with our European current competitors, the collaborators, build a xenon observatory with a broad science program. This is you can see it here if you read about it. 600 authors, 140 institutions to build a 100-ton scale dark matter experiment. And we're starting to hold collaboration working groups, so this is starting to get off the ground. Let's skip the rest of this and this oh yeah. And there's the show photos of the LZ group here at UC Berkeley. And the postdocs and this one. And the graduate students who just graduated this month. And the folks are learning and other Smith for this year, and other folks who've been to Berkeley and worked on LUX and LZ. Usually it's a kind of 50-50 combo between data science and faculty positions. And I also want to highlight a group that we work at very closely with at LUX physics division. Bill Bolsey, there's the project scientist, Kevin Musto, the head of the documented group in the physics division, and staff science Peter Stone, and Simon Fiorucci, who's the project manager for LZ. And first off, we are also working at LZ very closely, collaborating with them with our group. So I'll leave it at that and thank our sponsors. Yeah, I think you're right that the self-shielding, you could imagine instead of building like a 100-ton experiment, you could build 10 ton experiments. We certainly could take that strategy, and you're right that the self-shielding isn't getting enough anymore. Our backgrounds largely are just stuff that's dissolved in the genome, way down. Now that argument's not quite there for double beta decay. The main background system, high energy gamma rays that are more penetrating. So that's one reason to build one big detector. The other is just sort of operational. We're sort of one big detector and running it that way. You just, I think run into more operational complexities and you have many different detectors. Yeah, not really. Our scaling, okay, I used to always say it scales the surface area for the detectors. It's not really true anymore. Now that xenon device is starting to matter and we're starting to scale by volume, but there's no worse scaling. Yep, question. Bragg's law? Bragg's law? I don't. So that's really tricky. So the neutrinos, we can't shield them out, obviously. So you can ask, what can we do to get rid of neutrino backgrounds? We can't shield it out. And one idea, which it's very difficult and probably very expensive to execute is to lock in effectively on the direction that the dark matter is coming from. It's coming from roughly because our star, our sun, is going down towards Sagittarius, constellation. On average, there's a dark matter wind coming at us from Sagittarius, that direction. So if you could say focus more on stuff that's happening from the direction of Sagittarius, you could help reduce, basically do a better cut to remove background, get some improvement there. The question is, how do you get the direction of the nuclear recoil? Now here, we can't image the recoil, it's like micron track. We have no way in our liquid xenon project to be able to figure out which direction the recoil is happening. But in principle, you could have some other detectors that could tell the direction of that direction. I think in practice, that becomes, if you were to deal with a detector with tens of tons of mass to try to be better than say XLZD, the next experiment, while having, I think you're probably talking about $1 billion. So then it becomes a question of would you invest in such a technology in order to get somewhat below the neutrino fog, in order to get some directional information to see a signal which might be there. So it's sort of a cost-benefit question that I imagine we'll be taking up as a community if we don't see a signal. The trick problem. So yeah, so the core of the high voltage line is a graphite doped polyethylene, very high voltage. That's what connects to the cathode. Okay. And then in order to keep the field as controlled as possible so that they don't ever go too high, you have sort of a consistent grading of that voltage down to ground. Okay, so we have these rings installed with resistors between the rings, and each of those rings was at a progressively lower voltage. The challenge is to keep the electric field low as possible. And to do so, you need to grade down the voltage in the control in order that you don't have some gap at a very high voltage, a small gap, creating a lot of breakdowns in those. So we had to make all that work in a low radioactivity way, and it worked at low temperature. Yeah, so in helium and liquid neon, there's no conduction band for the electrons to go into. The electrons get into a so-called bubble state. The electron basically pushes away the other atoms around it. It creates an electron bubble. Bubble has a high effective mass. So basically, the number of noble gas atoms that it's supplanting. And they have to pull that bubble through the liquid. And that ends up just being very slow. Whereas in argon and krypton and xenon, you can actually promote electrons through conduction band and then move at much, sort of millimeter to micrometer. So the speed drops by 6 orders of magnitude. And you go from liquid argon to liquid neon. It makes it harder to do any detector using electron.